Okay, we know the length is 150, the free fall is 130. We can assume the mass is 70 kilograms, and when we are 30 degrees from the vertical, we are 10 feet off the ground. We can also assume we have 2,900 as our KS. So here we know that delta K and delta U are equal to 0 because the KS is equal to the U initial. The U initial is the potential initial. It's all potential at the beginning because you don't have any momentum and there's no velocity. The 1/2 mv squared is the KS that you have, and the mgh is the U initial. You just rearrange that to get your V, and you get 27. And then you move to the F net is equal to the T minus the mg, and you know that F net is mv squared over r because that's the perpendicular at this situation because it's at the bottom, it's the maximum, and that's equal to T minus mg, and you just go ahead and you plug in the values that you know from your assumed or your converted, and you get 1,875. And now we go to the more complex problem wherever you have it 30 degrees from the vertical. We have a situation where it's from free fall, where the length is right here, and then you have a further length that goes down afterwards, and there's different components of it. So here you see that you're adding them, and then you can rearrange it so that you have the h on one side. Here you go ahead and you do a geometry analysis of what angle or how it equates in, and you have L minus L cosine 30 is equal to H. You go ahead and you plug in your numbers and your conversions that you've had, and you also have to be careful to add the 10 feet in because of the fact that you're above the ground still, and that's the initial height. So you go ahead to the potential final, and the kinetic final is equal to the potential initial because at the very beginning all you have is potential, and in the middle you have potential and kinetic energy. So you go ahead and you use your mgh, your 1/2 mv squared that we're very familiar with, and you rearrange it into a velocity. So then you get 24 is your approximate velocity. We can then go ahead and plug that into our F net that we know, where we have the familiar equation from before, from number 2, the mv squared over r is equal to T minus mg, and you can go ahead and plug in the numbers that you've been given through your assumptions and your calculations, and you get 1,500. Over here, we can find the KS. S is equal to T, and that's what our equation is to find the stretch. You have 2,900 as the assumed KS, and to rearrange that, you just divide by that number, and we have the 1,800 from up here, from the original as if it's at the bottom. So that's the KS for the bottom, or the S at the bottom, sorry. This is the S for the one for the 30 degrees. You go ahead and do the same for the KS because it's the same rope. You're just dividing by that KS, and you have the 1,500 from the F net we calculated here. So now I'm going to show a video of the same function that I ran on my programming. So here we see different components of the force. This is the perpendicular and this is the parallel. And the perpendicular is dominating there and the parallel is at a minimum there, but there it's at a maximum. Roughly. Oh, there we go. So we can see it gradually moving back and forth. So we know that there's a parallel and perpendicular component within the force, and that at the bottom we have the perpendicular component dominating. So the velocity at the very bottom is the greatest because of the fact that the mv squared over r is the dominating factor. So the tension is also the greatest at the bottom because we know that it correlates to the K equals T minus mg, which is the correlating factor. Mv squared over r is equal to 1/2 mv. And then the little stretch, if you want to make it smaller, the Ks is equal to, you have to make it greater and the mass less. And perpendicular is at the bottom. Thank you.